G'day. This is a worksheet video on the algebraic proofs of Pythagoras Theorem. I have another worksheet video on the geometric proofs. There are thousands of algebraic proofs of Pythagoras Theorem, and on this worksheet I've just chosen 7. You can do all the proofs on this worksheet, but your understanding would be deepened if you used a geoboard as well. Algebraic proof number 1. If you form 4 right triangles on the geoboard, and we'll make the shortest side A and the other side B, and the hypotenuse of course is C. So the area of this square is C squared. Now the 5 areas within that square will be the 4 right triangles, which are identical, and this square, which has a side of B minus A. We start by making a right triangle, ABC. Now we rotate this right triangle 90 degrees anti-clockwise, 180 degrees, and 270 degrees. So we end up with 4 identical right triangles and a square in the middle. By looking at the square first, and I see the side of this square is B minus A, so that would be B minus A squared, and then 4 times half AB, which would be the 4 right triangles. I then expand this expression, which gives me B squared minus 2AB plus A squared, and then 4 times half AB is 2AB. I now have minus 2AB and plus 2AB. They cancel, and I'm left with C squared equals B squared plus A squared. Algebraic proof number 2 on the geoboard. We see we have 4 right triangles, and we have a square in the middle, which is obviously C squared. If we make the shortest side A and the middle side B, then the area of this whole square will be A plus B squared. And we just equate the whole area to the 5 areas within it. The area of the large square is going to be A plus B squared. We equate that with the 5 other areas within that square, that is, the 4 right triangles and the square. 4 times half, again it's half AB, and the square is C squared. Now we must expand A plus B squared, which is A squared plus 2AB plus B squared equals 2AB plus C squared. The 2 AB's cancel, and we are left with A squared plus B squared equals C squared. Algebraic proof number 3 on the geoboard. We have a right triangle, and this is a perpendicular, that is, it goes from the right angle and meets its opposite side at a right angle. Why this always produces two triangles which are similar to the large triangle, so that makes three triangles in all, I'll explain on the whiteboard. Here I have a right triangle, and I've marked the right angle, and I'm going to mark this angle here theta, and I'm going to mark this angle 90 minus theta, which it must be because of the angle sum of a triangle. Next, I'm going to drop a perpendicular from the right angle to the opposite side. I know I can do this with a compass and unmarked ruler. I've dropped the perpendicular by its construction, forms two right angles with this opposite side. And I think I'll call this triangle triangle 2 and this one triangle 3, triangle 1 being the original triangle. Now triangle 2 will have angles of 90 degrees, theta, and then because of the angle sum of a triangle, this will be 90 minus theta. Triangle 3 will have angles of 90 degrees, 90 minus theta, and this must be theta. Now I wish to summarize. Triangle 1 has angles of 90 degrees, theta, and 90 minus theta. Triangle 2 has angles of 90 degrees, theta, and 90 minus theta, the same. And triangle 3, it has angles of 90 degrees, theta, and 90 minus theta. These triangles are all similar by angle, angle, angle. Well, we actually only need two angles the same, because the third one will then be the same. What have we learned from this? That any time you drop a perpendicular from the right angle to its opposite side, you form two triangles which are similar, and they both are also similar to the original triangle. We're going to use this fact in algebraic proof number 3. The original triangle, PQR, to the smaller triangles, and I'll deal with the larger of those two first, SQP. And of course that's by AA or AAA. And the idea here is to write SQP. And then we note that QP is B, and that SQ, well, that's X, and SP, I've called that Z. And now we make a ratio that B over C in this triangle equals, well, that's X over B. If I cross multiply, B squared equals CX. Now the other triangle, this one, PQR, is similar to SPR. And of course that's by AA or AAA. Again, SPR. If we look back at the diagram, PR is A, SP is Z, and SR, well, that's Y. And now we're going to make a ratio A over C equals Y over A. Cross multiply A squared equals CY. Add the two equations. In other words, A squared plus B squared equals CX plus CY. Now I can factor this into C x plus y. But when I refer back to the diagram, I see that x plus y equals c. This is c squared. And I have a squared plus b squared equals c squared. This is Garfield's algebraic proof on the geoboard. We start with an original right triangle. I'm going to slide rotate that 90 degrees clockwise into this position. Because of the way we've constructed this, we know that this is a straight line and this is an angle of 90 degrees. Now we're going to join these 2 points, and this forms a trapezium, or what the Americans call a trapezoid. It has 2 parallel lines and 4 sides. The formula for that is base 1 plus base 2 over 2 times the perpendicular height. Well, we can see that base 1 is B, base 2 is A, and the height is A plus B. We equate that with the sum of the 3 triangles. Algebraic proof number 4 is known as Garfield's proof, that is, President James Garfield, the 20th President of the USA. He had a great love of mathematics, and this is a very neat proof. Triangle QST is constructed as a 90-degree clockwise slide rotation of triangle RPQ. Now draw TR. What is the measure of angle TQR? Well, by its construction, which was a 90-degree clockwise slide rotation, it must be 90 degrees. We equate the area of the trapezium formed to the areas of the 3 triangles. If you recall the formula for a trapezium, it is base 1 plus base 2 over 2 times the height. Now this was going to equal the areas of the 3 triangles. Well, this one here, which we said was a right triangle, half c squared. And then we have 2 right triangles, half AB. B1 plus B2, well, that's going to be A plus B over 2 times the height, which is A plus B, half C squared plus AB. If we double both sides, we get A plus B times A plus B, so that's going to be A plus B squared equals C squared plus 2AB. A squared plus B squared is A squared plus 2AB plus B squared equals C squared plus 2AB. 2AB's go out, and we are left with A squared plus B squared equals C squared. This is algebraic proof number 5 on the geoboard. We take this triangle and we slide rotate it 90 degrees about this point. And then we slide it back up. We know by construction that this angle here is 90 degrees. So we've got these two hypotenuse meeting at 90 degrees. Next we're asked to join this point and this point, and this point and this point. We then equate the quadrilateral formed to these two triangles. This one here, which obviously has a height of A, there, and the other triangle here, which obviously has a height of B, there. Algebraic proof number 5. Our original triangle, SRT, is slide rotated 90 degrees clockwise, and we form PQS. By our construction, this will be a right angle. Draw two lines, RQ and QT. I now see I have a quadrilateral SRQT, and I can equate that to two triangles within that quadrilateral, SQT, which is this triangle here, and RQS, the other one. We have a quadrilateral with diagonals at 90 degrees. The area of that quadrilateral will be half times the product of the diagonals. Well, the diagonals are C. Half C squared. SQT, well, the base is A, the height is also A, so that's half A squared. RQS, well, that has a base of B and a height of B. Half B squared. I just multiply the whole equation by 2, and C squared equals A squared plus B squared. This is algebraic proof number 6 done on the Geoboard. In this one we are going to rotate our original right triangle 90 degrees anti-clockwise, and we're going to make it disappear. But before we do, it's important to note that this square is B squared. If I took away the original triangle, then that would still be B squared. Join two other points, and I'm going to equate B squared with this triangle, half C squared, plus this triangle, this is B minus A, and this is B plus A, so that would be half B minus A times B plus A. Algebraic proof number 6. We start with the triangle PQR, and we draw a square on the B side. Then we rotate PQR 90 degrees anti-clockwise, and we form this triangle here, PTS. Note that if I shade this area, this will still be B squared, because I've taken from B squared this triangle and I have rotated it up to be outside it. So in this picture, this is still B squared. I have now drawn SR. And note that this is a right angle, being part of a square, and this is also a right angle as a result of our construction. I'm going to equate b squared with the area of these two triangles. Well, this triangle here will be half c squared. That's easy. The other one will be half times b minus a and b plus a, which is the height. Equation by 2, I get 2b squared equals c squared plus the difference of squares. B minus a times b plus a is b squared minus a squared. Take a b squared out of the equation to get b squared equals c squared minus a squared plus b squared equals c squared. Algebraic proof number 7. Here is our original triangle, and we slide rotate this triangle around this point 90 degrees clockwise. Now we join two pairs of points. This pair and this pair. We equate these three triangles with these two triangles. Algebraic proof number 7. We start with our triangle PQR, slide rotate that 90 degrees clockwise, form STP. So this will be a right angle, this will also be a right angle. Draw two lines, TR and SR. Look at this diagram in two ways. I can see it's the addition of these three triangles, or I can see it is the addition of these two triangles. I'll deal with the three triangles first. PQR, well, that simply will be half AB, and STP will also be half AB, and TQR, well, the base is B and the height is B minus A, so it's half B times B minus A, and that equals triangle SRP. Well, SRP has a base of C and a height of C, so that's just half C squared. And triangle SRT has a base of A and a height of B minus A, so that's half A, B minus A. Multiply the whole expression by 2 and we get AB plus AB plus, expand that, B squared minus AB equals C squared plus AB minus A squared. Let's gather like terms here, and we can see we have B squared plus AB equals C squared minus A squared plus AB. Well, we can knock out the AB on both sides and bring over the A squared, and we get A squared plus B squared equals C squared. Okay, that's the end of this worksheet on algebraic proofs of Pythagoras' theorem. If you want to have a look at some geometric proofs of Pythagoras' theorem, I also did a worksheet video on that. And other than that, there's plenty on the internet about this as well.